Okay, so for Gauss 12, so this problem is going to be an immediate application of this theorem that we have that says the electric flux through a boundary surface is directly proportional to the amount of charge on the inside. So most of this problem is a matter of just computing how much total charge there is on the inside of this sphere. Now the sphere has radius 2.5, and the charged particles are, well, they're kind of distributed throughout space, but just at the integer coordinates points. So really, this is just a counting problem. You just got to figure out inside of this sphere of radius 2.5, like so. How many points with all integer coordinates? So what I'm going to do with this is just kind of, I'm going to draw little pictures, right? But I'm going to start by looking at, at z equals 0, because that's one of the integer coordinates, and then I'm going to draw that picture over here. What does that cross section look like in the xy plane? And then after I've done that, then I'm going to do z equals 1. We'll look at that cross section, draw its picture in the xy plane, and then we'll look at z equals 2. And then, now of course, z equals 3 is a swing and a miss, right? There's nothing there. There is no cross. The only radius is only 2.5. And then, of course, there's also z equals -1 and z equals -2, but of course these are going to be the same because of symmetry, and these are going to be the same because of symmetry. So I really only have to count. I only have to go to the trouble of drawing these, and the rest is arithmetic. Does that make sense? Yeah. Okay, so let's do one. Let's talk about z equals 0. So what's the cross section? If I've got this thing has radius 2.5, then the equation for the sphere is x squared plus y squared plus z squared equals 6.25. It's 2.5 squared. Right. So if z is equal to 0, that goes away, and you just get a circle of radius, 2.5. All right. And I'm just going to literally start drawing lattice points. Maybe I'll do that with this pen here. So there's one, there's one, there's one. Now there's another one over here, but that doesn't count. Hey, that's 3, that's outside. Okay, then now of course also there, 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 there. Now clearly these points are also in it. Why? Because, well, that distance there is square root of 2. It's like 1.4 something. That's definitely less than 2.5. What about this point? Now, this is a close call, like 1, 2. Is that in? Like, we have to decide, is that in this circle or not? In other words, is its distance from the origin more or less than 2.5? Well, it's the square root of 5 is the distance. And you got to pull out a calculator and see what's the square root of 5. Well, now, on the other hand, different point of view you could take is, well, the square root of 5 is clearly less than the square root of 6.25. So it's going to be less. It's like 2.2 something, as I recall. So that's in. And that means that so is that one, and 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 that one. Now, what about 2, 2? Well, let's see, 2, 2. Well, square root of 8, that's 2 square root of 2. That's 2.8 something. That's outside. So that's going to be out here. That doesn't count. Similarly, anything with a 3, so 1, 3 is out for the same reason that 0, 3. And I claim, in fact, this is all the lattice points we have in there. And now you just literally count them. Right? And it looks like that's 21, if I'm counting right. Okay. All right, so in z equals 0, we found 21. Okay, now proceeding along, what about where z is equal? This is z equals 0. Let's look at where z is equal to 1. Where z is equal to 1, the equation becomes x squared plus y squared equals 5.25. So x squared plus y squared equals, and you got to figure out what is the square root of 5.25, because that's your radius. And okay, it's less than 2.5 by a little bit, but it's more than 2. So it's somewhere in the 2.5 range. I'm going to draw a slightly smaller circle here. And again, you have to play this game, and we got to just decide, which points are in and which points are out, and it's just counting. So yeah, hopefully you're getting the idea here. And let's see, let me just see if I can. So that one, all of these are obviously in. Now again, we got to reconsider. Now it was a close call to 1, 2 previously. Square root of 5 is the distance to the origin. Square root of 5 1/4 is the radius of the circle, so it's barely in. So yeah, that one, that's in, that's in, that. And so all the ones that had been in are still in. That's kind of weird. Is that right? Yeah, it appears to be right. So, okay, well there's another 21. That means there's another 21 here by symmetry. And then, anyway, same game, z equals 2, which means you'll have square root of 2 1/4. You can finish this off, yeah. Yep.
So after you've done counting, you plug in the square equation?
Yeah, oh, excuse me. Yeah, so that's right. So after we're done with the arithmetic, then we use this. Let's see, where did it go? Yeah, here you go. Well, let's see, where I first put it. Yeah, so electric flux is just you count the total charge. Now, each particle in that list had the same charge Q. So the total charge is going to be like, I forget exactly. I want to say it's 80-something, but it's, anyway, some integer number times Q, and then that's for your charge, and then divided by that constant. And that's your flux.
You don't need to know the cost.
No. This is just, you just write that down, and what the value of that is not, yeah, that's a physics thing. I'll let physicists worry about that. Yeah. All right. Does that make sense?
Yeah.
Okay. Okay, should I stop the recording, or do you have more questions about this?
You can stop.
Yeah, okay. All right, let's see here.